Good afternoon, everyone, and welcome to today's webinar. Thank you for joining us as today we talk about cold weather concrete, and we have registered to go to over 30 sites around Pennsylvania today. We were originally going to do this webinar in October, then moved it back to November, thinking that'll be closer to the cold weather. So I was very happy to schedule this webinar today, which turns out to be a very beautiful, not cold day. So if a few people can't join us because they're too busy making or placing concrete, that's a good problem to have. But what we're going to find out today, eventually the cold weather is going to come, and it doesn't have to be brutally frigid for us to have to do some things different to make sure that our concrete is protected and our businesses are protected. I'm Jim Casilio, Director of Technical Services for the Pennsylvania Aggregate and Concrete Association. Also as a panelist today, Susan Armstrong with Central Builders, who chairs our PACA Concrete Technical Community. Susan is standing by to take your questions, which we're going to go over at the end of the webinar. So if you have any, feel free to type them in the questions section or the chat section of your GoToWebinar control panel. We also have some handouts today, and if you click on that little orange or right arrow up on the upper right hand side of your screen, if your control panel's not exploded, it will bring your control panel back into view clicking on that arrow, and you'll see under handouts where it says 5 handouts. One of them is the PACA antitrust policy. So as with all of our association meetings, we will conduct this electronic meeting in accordance with the PACA antitrust policy. But there's also some technical documents that are available for you to download and print right from there. And so you'll see those 5 handouts on there. This is the first document. This is the concrete difference, placing, protecting concrete during cold weather. This document was developed by our PACA Concrete Technical Community. Our immediate past chairman, Brian Scheffler, was instrumental in getting these publications beginning to be published, developed, and published. This is an outreach from these documents, today's webinar, so we appreciate Brian's work. Brian should be very, very proud of the work he's done. He's on our webinar today with us, and we're going to be using this and referring to this often. So if you want to right now, you can go to your handouts, you can download a copy of that, you can print it out, because there's 2 charts on there we're going to be referring to today. And of course, you can get that and print that out and use it past today's webinar. This and all of our publications are available on our specifyconcrete.org website. You'll see it listed up there and on the bottom right-hand side of all of our screens, and we'll show you a little bit more about that later on. Second document we're going to be referring to, which is a good handy reference for cold weather concreting, is also included in your handouts. This is NRMCA's CIP 27 cold weather concreting. You can download that from their handouts. You can download that from specifyconcrete.org. However, you can't print that out. You've got to get that directly from NRMCA. That is their policy, but it's a great reference that every concrete producer, every concrete contractor should have for dealing with cold weather concrete. And the third thing we're going to be referring to, and this is going to be the bulk of our presentation, we're going to refer to ACI 306R, and that's the Guide to Cold Weather Concreting. Now, excuse me, this is a guide, and this is not a standard. A guide, what's the difference? Well, ACI Committee 306R also puts out a specification, and the specification is about 5 pages long. It's written in very terse language. It's exactly what needs to be done, but a guide's a little bit different. It goes into the how, whys, and what's in much more detail. You can call it a guide, you could call it a best practices document, you could call it a state-of-the-art document. However, it's important. It's important for all of us, whether you produce concrete, whether you place concrete, whether you're a general contractor, construction manager, engineer, or designer. There's sections of this guide that apply to everybody and to all that. And it's important that you know that. We're professionals in the industry. where it's not just the engineer who's responsible for knowing what's in this publication. This is the state of the art. This is our best practices. This is where all the knowledge applies. So when we're doing concrete in colder weather, we all should be familiar with this document. And the reason we should be familiar with the document because that's going to help us not only protect our concrete, but it's going to help us to protect our business. And nothing sums it up better than this one statement in ACI 306R in chapter 3.1. It's a pretty all-encompassing sentence. It says short-term gains in construction economy on protection should not be obtained at the expense of long-term durability. Now think about that for a second, what that implies. To me, it means that we should know whether you're producing, placing, a contractor on the job site, ready-mix producer, a concrete contractor, you should know what you need to do. Because if you're cutting any corners, and if you're doing you're not doing everything you need to know, and there's problems afterwards, it can come back to you. Trust me, the first time you see this sentence, you don't want to be sitting in a courtroom where an attorney hands you a copy of 306.R and asks you to read that for the court, please. You should be familiar with what's in that document. So we're going to do that today. Here is the prelude to 306R. And it says what the goals are. You can read through that. A, prevents damage to concrete due to freezing in early ages. Ensures the concrete develops recommended strength. Maintain curing conditions for strength development. Limit rapid temperature changes. And provide consistent protection. But also, it's important, look at that last sentence there. Concrete placed during cold weather will develop sufficient strength and durability to satisfy the intended service requirements when it is properly proportioned, produced, placed, and protected. So those 4 P's, proportioned, produced, placed, and protected, that's what we're going to go over today. But before we do that, let's talk a little bit about the first half of that sentence. Develop sufficient strength and durability to satisfy intended service requirements. So before we talk about cold weather, let's refresh ourselves of how concrete develops sufficient strength and durability, whether the weather's cold, whether the weather's hot, or it's a surprisingly beautiful day like it is today. All right, here we see a picture of unhydrated cement grains. All right, when people say cement is a glassy, crystalline structure, you can see that here. They look like tiny little sugar cubes, tiny little grains of salt. That's what cement particles look like at the microscopic level. So here you see hydration beginning. I used to be able to try and explain to people how concrete works. You mix water with the cement grains and little fingers grow out of it and they intertwine. Well, now we have a picture of those little fingers growing out of cement grains and begin to come in contact with each other. The more these little fingers, the crystals grow, the more they touch their neighbors, the more they intertwine with the neighbors, the stronger the concrete gets. That's what gives concrete its strength, these tiny little fingers growing and connecting with the neighbors on that. Now, you can see the dark spaces around those hydrating grains of cement. Those dark spaces are voids in there. We want to fill those voids in. So we want to fill them with either hydrated cement or something else that's durable, because the more we fill those voids in, the more dense our concrete is and the more durable it is. So you can see that strength and durability are related, but they're a little bit separate. Definitely related though. Here's a slide looking at it in even a closer level. The grayish green background you see there with the little kind of pot marks in it is the surface of one of those cement grains we looked at earlier. And the pot marks you see on it where ions have left that, have gone into solution around that, and have now precipitated out and forming the CHS cement crystals we see on the right center and right hand side of our screen. Those are actually those little fingers, those little crystals are beginning to grow on a grain of cement, and they're growing from what was taken out of that grain of cement and gone into solution around it. Pulling back and doing it at a much further back scale, we look at it at a different level. That dark area on the lower half of your screen, that's a sand particle. And what you see all around that are the cement paste. Looks like a mountain range here now. Those are those little needles at a way different scale. That's what's forming around it, making our concrete hard and durable. That process, hydration, is affected from the outside by two things: temperature and the amount of moisture available. This is an interesting slide. Look at what happens to strength development: concrete at 73 degrees, concrete at 55 degrees, and concrete at 40 degrees. We all know that the strength is going to be different on that. But now look at just that the strength is lower on the early ages on the 55 and 40 degree concrete. Notice how the shape of the curve is different. So what that's telling us is that temperature, lower temperature effect is actually changing the parameters of that hydration reaction. It's occurring at different rates. There's different chemistries going on there because the temperature has affected that. Hence the different shape of the strength gain curve. Second way we're going to affect high strength of concrete from the outside is by denying it moisture. Here you see concrete made from one batch, cylinders made from one batch of concrete, but they were cured differently. One was kept in laboratory air for its entire time. One was kept in moist curing for 7 days, then in laboratory air. One for 28 days moist, then in laboratory air, and one moist cured for the entire time. Look at the difference of strength over the long term. So when we deny moistures to those little crystals we saw in the picture earlier, they stop growing, and they stop growing immediately. Look what happens here. We took concrete that has the potential to reach 8,000 psi, and only by denying it moisture, we ended up with it being somewhere about 4,000 psi. So in other words, congratulations. We did not curing this concrete gives us exactly half of what we paid for. Many times if we bought anything, if we do anything and we got half of what we paid for, we would not be happy. But unfortunately, we see concrete not being cured routinely. What are we doing? We're getting exactly half of what we paid for. So let's talk about cold weather concrete. The most extreme will be occasion if we freeze concrete. That's really, really difficult to do. We'll show some examples of some people doing it, but that's hard to do. You don't have to freeze concrete to make it weakened, but it can be done. One of the telltale signs of frozen concrete is you look at the surface, and the surface looks like a dried out fallen leaf, all wrinkly with all sorts of little lines and patterns in it like that, a dried out lake bed, whatever analogy you want to use. Very distinctive appearance to the surface. Second telltale sign concrete being frozen is a very, very white appearance, white like a sheet of paper. Here you see a little bit of that white along with the telltale signs, excuse me folks, telltale signs of that kind of cracking, dried leaf kind of pattern that's going on right there. Not all the concrete froze. You see on the edges it didn't freeze, but you got one frozen spot right there. It's white, and you see the cracking pattern in it. You also see a lot of cracks, look like plastic shrinkage cracks going through it. That's very common. It's a very telltale sign of it because in the wintertime, when the weather's cold, we drive the moisture out of that concrete really quickly, way too quickly. Now, we don't have to freeze concrete to weaken its surface. Here's an example. You can see again that kind of close pattern, large size crazing, drying shrinkage, plastic shrinkage cracks over the top of it. This concrete is a driveway that was not protected. And here's the results a couple days after it was placed. It was placed in cold weather and not protected. Dried out, subject to no strength gain because of temperature effect. Remember our chart we saw earlier? And here's what we end up with. Now here's the paradox, folks. The part of concrete we need to be the most durable is the surface. The part that dries out the first, again, no strength gain, is the surface. The part that's subject to colder weather, lower temperature gain, is the surface. So you don't have to freeze concrete to have it weakened. Most time, 99% of the times, cold weather damage comes to not frozen concrete, but just extremely weakened concrete like you see in this sidewalk here. The definition of cold weather, ACI 306R, is when you have a time when the temperature falls 40 degrees during the protection period, that's cold weather. That's when the cold weather rules kick in. Where's our protection period? We're going to talk about a protection period anywhere from 1 to 7 days today. It at least has to be 1, but it's up to 7. So if you have 1 day during that time where it's going to fall below 40 degrees, you've got to do something to protect that concrete. All right, let's get back to our 4 P's and let's go through them one at a time. The first one, proportioned. The goal of every mini mix producer is consistency. We want to give concrete with consistent workability, consistent set time, consistent strength gain. To do that, summer to winter, most producers really don't need to change their proportions. However, what they commonly do is we'll reduce our percentages of pozzolans, slag cement, or fly ash in the colder weather as opposed to the summer. In the summertime, high dosage of those are great. They give us workability, they give us finishability, they give us a large finishing window, nice slow strength gain. They counteract all those bad effects we see in high temperatures. However, in colder temperatures, they're going to be counterproductive. They're going to go against what we're trying to do, is get a nice good set and strength gain. Now, other way to do that is by added cement or just specifying a higher PSI, which has more cement. That's okay, but there's some bad things that come along with it. You get extra shrinkage and extra curling anytime you use extra cement where you really don't need. Not to mention, it's sticky, the workability goes down, tough to finish. And of course, we're going to use air and train concrete, except when we have a trowel finish. Excuse me. All right, the most important thing we can do on proportions is accelerating admixtures. They help normalize set time and initial strength gain. But remember, they're supposed to be used with and not a substitution for adequate protection. Let's talk about accelerating admixtures. We'll talk about the 4 commonly types of accelerating admixtures that are available to us. First, good old calcium chloride, bagged calcium, flake calcium, whatever you want to call it. It's effective, it's very low cost. By all the standards, it's limited to use of 2% by cement weight, but there's other limits on it. It's not to be used on any concrete, exposed concrete containing or steel reinforcing, or any concrete at all with pre-stressing steel in it. Because of the bad effects of increasing corrosion in rebar, most commercial specifications outlaw the use of any admixtures containing calcium chloride in it. They're just not allowed on any commercial specs, on commercial jobs. That's probably well over 90% of them. Now, your second option is a liquid calcium chloride accelerating admixtures. Again, cost effective, but again, this also has the same limitations in use as the bagged calcium. Our next type, that's the most common, non-chloride accelerating admixtures. They can be used at high quantities without any detrimental effects to the concrete. They work very well because you can use whatever amount that you feel you need that day. They are, of course, more expensive than the chloride-based accelerators. And the last one talked about in ACI 306R is what's called cold weather admixture systems. These are admixtures, or most often combination of admixtures, that depress the freezing point of the mixing water and increase the rate of hydration. They have their own separate ASTM for approval. That's 1662. All the other admixtures, ASTM, I think is 494 is their approval spec on it. These are separate. It's a separate category. They are very expensive, and they're most often reserved for extremely severe cold weather applications. All right, we've talked about proportioned concrete. Let's get on to our next P, produced. Table 5.1. Here's that first table that I asked you to refer to on your concrete difference cold weather document. A copy of this table is right on your first page, and this is probably the most important thing we're going to go over today. It has a lot of information on for both the producer and the contractor. So, produced. If you're a ready-mix contractor, there's your limits. In the middle there, it tells you the temperature as mixed. That's the temperature you have to produce that concrete at for your different size of whatever you're pouring, either 60, 65, or 70 degrees. Those are your minimum concrete temperatures at the plant. So how do we do that? Picture of an infernal therm, that's what it's commonly called. There's many different brands that make these heaters. This is a unit that can both heat and store hot water at the same time. We need to have a lot of hot water at a concrete plant. The difficulty with that is even on a moderate busy day, you can't heat it as fast as you can make it as it goes out. Excuse me, you can't heat it as fast as you're using it. So it goes out the door faster than you usually can heat it. So you have to start the day with a good supply of hot water. Here you see probably 6,000 to 7,000 gallons of hot water, all primed up, all ready to go. So we need that, a lot of it available at a consistent temperature. Now, some of the building specs and some of the code you'll see, it can't say mixing water above 140 degrees. Well, 306R says over 140 degrees, you got to be careful. You don't want all that hot water coming in with nothing but the cement early on in your batching process, so you may have to alter your batching process. We still see some specifications out there that limit the maximum mixing water temperature. I consider those to be outdated and bad specifications, because it is very common that you're going to need your mixing water to be well above 140 degrees to make those requirements that we saw in table 5.1. There's no way to do it other than that, because what we're doing is taking the mixing water, which is the smallest amount of weight or mass of all of our concrete ingredients, somewhere 250 pounds of water a yard, that we're going to add to it, and we're going to ask that to heat up to 60, 65, or 70 degrees everything else. Well, everything else in a yard of concrete weighs total about 3,900, 4,000 pounds. So we're taking 250 pounds of hot stuff and asking it to bring up the temperature, everything else that's in that. So sometimes we got to be, very often we got to be a whole lot higher than 140 degrees. And on your really cold days to hit those temperatures, we might have to heat our aggregates a little bit. All right, so we proportioned, we produced our concrete. Let's talk about placing it. On line 1 there, you see the required placement temperatures. These are the minimum temperatures that that concrete has to hit the job at and be placed at. All right, so if you're pouring a 12-inch or less section, it's got to be 55 degrees. If it's 1 foot to 3 foot thick, it's got to be 50 degrees. Some other considerations for placing. 306R says usually you don't have to worry about heating your formwork unless it's really cold. They use 10 degrees. Some specs require everybody to heat up the steel or everything else that's in the concrete. Well, 306R says unless you've got stuff that's bigger than a 4 square inch area in section on it, you really don't need to heat that up. They do, however, recommend that you place concrete at the lowest possible slump. Why? Because even a little bit of water added can retard our set time. Well, what's that doing? That's counteracting what we're asking our accelerator and all the heat we're putting in there to do that. So we want to try not to be pushing that concrete in 2 directions. Now, Here's the hard part. 306R does recommend, as well as the specification 302 for concrete slabs on grade, is to have your subgrade temperature when you're pouring on a subgrade, either inside or outside of a building, to be above 32 degrees. That's many, many times difficult, and there's a whole lot of concrete that goes down on subgrade that's below 32 degrees. That's not what's supposed to be happening. All right, so we proportion produced and placed the concrete as we're supposed to. Now we have to protect it. What temperature do we have to protect it at? Go back to our table 5.1. It's the same temperature as it's placed at. Depends on our size of what we're making. If we're 12 inches or less, we've got to maintain the temperature at 55. If we're 1 foot to 3 foot, our minimum dimension, we have to maintain it at 50. Next question you're going to ask is, how long we're going to maintain it at? Chart table 7.1 on page 2 of your concrete difference cold weather document. How long we have to maintain it at depends upon its exposure and its loading that it's going to be carrying. So, line 1, no load, not exposed. Where is that? That's pretty much interior floors. Those are the only thing that's not going to be exposed in Pennsylvania, and it's probably not going to have a load on it, interior floors. Even with that, even if we accelerate the set of that concrete, we still need to maintain that protection, either 50 or 55 degrees from chart 5.1, at least 1 day, probably 2 days. Let's look at item 2, no load exposed. What does that cover? All your exterior flat work, your small walls that are just kind of carrying themselves but not much load on top of it. Look at the protection period for that. Even if we have to accelerate that, we're going to have to maintain protection 50 or 55 degrees for 2 days or 3 days. Your third one, partially loaded exposed. These are building walls, exterior columns, anything that's carrying a load. Real quickly, we see the protection period jump up on that. And line 4, that's fully loaded. This is formwork that requires support while the concrete's being placed. All right? We're not going to talk about today. This is pure structural concrete. Structural columns, floor for buildings where you're going to be building on top of it. You have formwork. It's supported. That's the key to get you in line 4. Supported formwork like that. There's all sorts of rules and regulations for that. That's certainly above what we're going to be talking about today. So that's how long we need to protect it. How do we protect it? 4 different ways. The first one, heated enclosures. Probably the best, probably the most expensive, but as you can see in these 2 pictures, these guys are dealing with everything in that line 4, fully supported structural concrete. So they have a lot of rules and regulations on them, what they need to do. Next is a portable heating unit. This unit here, this is a picture of I-95 currently under construction in Philadelphia. These are portable heating units. These things are great. They do the job. What you have there is a portable furnace, heating coils, 1 roll in, 1 roll out. You fire this thing up, you set what temperature you want it to be, you put your coils over your concrete, bridge deck, roadway, subgrade, whatever, throw a bunch of insulated blankets on top of it, fire it up, you're good to go. You dial in what temperature you want. So if somebody says to you, oh, there's no way we can protect it, absolutely no way we can protect it, yes, you can, all right? They're expensive, but they do work, and they do work very, very well, and they are being used. Next option is electric insulated blankets. All those of us who do PennDOT work, do accelerated patching, knows that these are requirements. No way are you opening a roadway to traffic in 4 hours, no matter how hot the night is, unless you're using these insulated blankets to kick off that reaction to get our strength earlier than later. They work very, very well. Not as good as our previous 2 examples, but they do provide heat. As we're going to see here and there, there's going to be some instances where we're going to have to add some heat to things that we don't normally think we do. And our last one is good old-fashioned insulated curing blankets. These are the most economical, excuse me folks, but they are limited. They're limited into use, and many times you're going to need a whole lot more than you think you have. It's a cold day, that guy's freezing out there, he's counting his blankets, he's making sure he's going to have enough. Insulated blankets. ACI 306R specifies minimum R values. It also lets us know that for any concrete placed on the ground that's 8 inches or less, insulated blankets is not enough. We need to be adding heat to it. That's a shock for many of us. Now, some quick and dirty research I did for preparing for today's webinar, I found that the R value of blankets, insulated blankets, varies a lot, anywhere from 2.8 to 7.5. Of course, you get what you pay for. So be careful when you're knowing what your R value of your blankets is, because it sure does vary a lot. And like we said before, most times you're going to need more than is commonly used. So how many do we need, and where do we need to use those? Fortunately, the guide has some information for us. First thing, let's talk about concrete on ground. There are charts in ACI 306R that tell us for our different mixes and the temperatures that we have based on the thickness of what we have. What is the R value of insulation we need to provide that'll give us this protection, in this case for 3 days. Now I pulled 2 charts off of there. One is a 500-pound cement mix, one is a 600-pound cement mix. And let's say the 500-pound cement mix, 3,000 psi. The 600-pound per yard mix, let's call that 4,000 psi. On both of these, you'll see that if your section on ground, on grade, is 8 inches or less, insulated blankets are not enough. Requires additional heat to keep it at 50 degrees, let alone keep it at 55. But look closer here now. Let's look at the top chart. Let's go down to that third line where it says slab thickness of 12 inches. Let's say we're pouring a 12-inch footing on grade, or we have something 12 inches thick on grade, a grade beam. For 42 degrees temperature, we need an R2. That's 1 blanket. If it's going down to 36 or below, we need an R, or good down to 36 is an R4. That's 2 blankets. Go all the way over to the right. Let's say it goes down to 24 degrees, and even it's been a mild fall, we've had some nights where it's gone down to 24 degrees. If I'm pouring something 12 inches thick on grade, it tells me I need to give it R8 insulation. That's probably 4 blankets. Now, how many times have you seen 4 blankets put on anything, let alone only when it's 24 degrees out there? So these are the rules that we need to know. They are out there. Now, what's that showing me is that insulated blankets for concrete placed on ground are very limiting. Now, let's talk about concrete walls or slabs that place above grade. Much easier to use insulated blankets there to maintain what we need. However, just as before, we may end up with a few more than we normally think we do. Again, 306R gives us charts for that. Here you see one of those. I pulled out one of that for to talk about today, and that's a 600-pound mix. So let's say we're using 4,000 psi concrete. We're pouring a 12-inch wall, and it's going to go down to 20 degrees tonight. What do we need to protect it? So we go over to our chart here, and we go there. That's going to somewhere between us an R4 and R6, so we're going to need somewhere about an R5, which is at least 2 blankets on that. Now, what's curious from this chart is, let's say we have a colder night, and they're coming, then it's going to go down to 10 degrees. Even at that, you're going to need to get probably 3 blankets on that. You're going to need between an R6 and an R8. And on this chart, the R values are in parentheses. They're behind the metric units. What's also interesting on this chart, if you look up higher on it, even if it's a night that's just below 40 degrees and you have a 12-inch wall poured, you're still going to need an R2 or probably one blanket on it. Now, how many times do you see concrete protected when it's 38 degrees out there? Not often, but however, according to the 306 guide, we need to be doing that. One last thing 306 recommends for us is we protected it now 1, 2, 3, or 7 days, however many days it is. We can't just throw that off real quick and let it go out back to temperature. They limit the temperature drop in the first 24 hours. So 12-inch section, no more than 50 degrees. 1 foot to 3 foot section, no more temperature drop than 40 degrees from your protection temperature to the end. And they're always concerning about what temperature is the concrete. They're concerned about that temperature of the concrete right at the interface between the blanket and the top of the concrete. All right, in addition to protecting the concrete, another thing we have to worry about in cold weather is the quality of testing that's out there. In hot weather and cold weather are the two times of the year we see that the testing problems frequently that are out there, they are widespread, come back to bite all of us. So the picture you see on the left-hand side, yep, those cylinders sitting there in an inch or so of snow without the top on them. So they have not been kept at the right temperature, nor they have moisture on it like that, protected from moisture loss. But yep, there they are. They'll be just fine to test now, won't they? Now, this slide is courtesy of our friends at NRMCA, but we got to take some credit or responsibility or blame for this, because the picture on the right-hand side is from one of Pennsylvania's finest bridge projects. You can see it's cold weather. Everything is brown and gray out there. There's an insulated blanket all wrapped up on the side of it, and there sit force test cylinders out in the cold weather. Nicely done. All right. I told you earlier it's really, really hard to freeze concrete. These guys did that. Cylinders arrived and the lab said, hey, let's break these cylinders. We need breaks today. Somebody was wise enough to say, what the hell happened to the top of these, and take a picture of them. Yes, these cylinders actually froze. The telltale whiteness on that. And if you look at the picture on the right, you can see that kind of dry leaf pattern on there that shows that even though that cylinder on the right didn't freeze, it was damaged, it was weak in the concrete, because the water that condensed on the top of it, it made that, that froze and made that pattern of signing on the top of it. To review real quick what we need these cylinders to be kept at. All cylinders on a job site between 60 and 80 degrees, prevent moisture loss, not disturb until 8 hours after final set, and they can only remain in a job site for 48 hours until they're transported to the lab for final curing. That's all cylinders. Now, standard cure cylinders. The cylinders, what are standard cure cylinders? Where are they used? Well, they're used to determine whether any of us get paid or not, and to check the quality of the concrete. So the requirements for that is they're cured at 60, 80 degrees initially, then they go into the lab 73.5 plus or minus 3.5. You see a lot of field cured cylinders out there. Now, the idea behind field cure cylinders is the initial cure is the same, 60 to 80 degrees, but then they go out and cured same as a structure, and I use the word same as in quotation marks. You see on the left, oh, we'll spray these cylinders with some curing compound, they're fine. But on the right-hand side, here's what happens often. That bridge deck's being protected nice and wet with the wet burlap. Why are those cylinders white? Why aren't they getting any water? Are they being cured the same as the structure? No. ACI 306R has addressed this finally, and it said in this statement in chapter 8.2, used to be we thought field cure cylinders were the way to monitor stuff in cold weather. No, they're not. It is inappropriate to use field cure cylinders to see how you're taking care of that concrete in colder weather. You got to measure what that actually is concrete doing. So field cure cylinders don't work no more. And this is a welcome adjustment and improvement in ACI 306R. All right, here's an interesting picture and a question for you. I showed this picture to a couple hundred PennDOT inspectors at a winter school this past February. It was a February day, about 25 degrees in the morning. So I gave this scenario to them. I says, okay, Here's a gentleman making cylinders today, 8 o'clock in the morning. He did everything right. Got an air and slump. He tested his right. He made all his cylinders properly. He's finishing them off. He's going to cap them. And I asked these 200 inspectors, what's wrong with this picture? And I said, remember, he's doing this today. So that day was 25 degrees. This morning it was probably upper 30s this morning. So we could say, what would be wrong with this picture today even? So he's going to take those cylinders and put them in that curing box. What's wrong with this, and nobody in the room got that because this looks like he's doing a pretty good job, and this gentleman is that these cylinders must be kept between 60 and 80 degrees at all time. If it was 25 degrees that morning or 38 degrees this morning, that curing box is 25 or 38 degrees. Those cylinders are not being kept between 60 and 80 degrees from the time they're born till the time they go into the lab. They're violating the specifications. There are specifications on us as concrete producers. There's specifications on us as concrete contractors. There's also specifications on the people doing the testing out there. However, I bet you a report was issued for the cylinders that said everything was done properly according to specs. No, it wasn't. And we all need to be eyes and ears out there in the field, because we don't want issues with testing coming back to be issues for concrete when it really is faulting testing. And an initial curing of test cylinders is a widespread problem, and it really comes to bear in hot weather and cold weather. Because it's such a widespread problem, Concrete Technical Committee has published another document. This is also in your handouts, also available at specifyconcrete.org. Please get a copy of that, download, print that out, keep it handy, share it with anybody you need to do. This shows you all the rules, what needs to be done to address this widespread problem of making and curing concrete test cylinders in the field improperly. Where is all this information available? Here is a picture of the homepage of specifyconcrete.org. All the technical documents we've gone through today and this webinar are all available on the Technical Center of specifyconcrete.org. And it's the same thing that you've seen on each one in the bottom right-hand corner of your slides. So in review, cold weather concrete. Use air and train concrete, except when trial finishes. Use accelerator as needed and specified and within specifications. Keep all that nasty stuff away from our formwork before we place the concrete. Get our subgrade above freezing, easier said than done. Place concrete at the lowest possible slump. Make, produce, and place concrete at or above the minimum required temperature, and maintain that temperature period for our required protection time for the entire part of it. When we're done protecting, we don't want really rapid temperature changes, and we want to be our eyes and ears out there and make sure that there's proper testing, handling, and making of cylinders being done in the field. So before we get to any questions, I want everybody to know about two educational opportunities we have coming up. December 5th, a webinar on ASR, talk about the new PennDOT ASR specification. And even if you're not doing just PennDOT work, this is going to spill over, and it has spilled over into the commercial side of things. So please feel free to join us. In your handout is a document that'll give you links to register for both our ASR webinar December 5th and our Concrete 101 and 201 classes. We brought those back last year to great success. If you want to learn a little bit more about doing concrete mix designs, if you know nothing about doing concrete mix design, this is the class for you. You can show up in the morning and we will crank you through a couple of concrete mix designs. We've added the 201 this year. We're going to talk about self-consolidating concrete, lightweight concrete, pump adjustments. We're going to take it up to the next level of mix design procedures. But Concrete 101's going to be 3 classes around the state, 1 west, 1 central, 1 east, and then the next week in Harrisburg is Concrete 201. So with that, Susan has been standing by to take in and review all your questions. What questions you have for us today, Susan?
One of the first questions I got was, if my concrete does freeze, how much strength can I expect to lose?
Great question. Depends when it froze. If it's able to get some strength before it freezes, you might be okay. What they found, concrete can withstand one freezing and thaw cycle with not much strength, say 500 to 1,000 psi. Some recent research said it should not be subject to repeated freezing and thawing cycles till it reaches 4,000 psi. So it really depends where and how quickly it froze. If it froze early, you're in tough straits. If it froze later, it should be okay.
Okay. Second question for you is there such a thing as an antifreeze admixture?
The cold weather admixture systems that we talked about earlier, they have been kind of mislabeled as antifreezes. There's real no such thing as an antifreeze. They do lower the freezing point of the concrete mixture of the mixing water, but it's not going to prevent that from freezing. So for really severe conditions, you need to use that, but you're also going to have to put protection along it to maintain that. There's no way out of the requirements of 306R just by placing some admixtures into the concrete. It just unfortunately doesn't work that way.
Okay. One of the last questions I have already is, does the additional curing improve other properties of the concrete? So am I better off to just cure longer?
You're always better off to cure longer, and in fact there's some specifications require if the temperature falls below what it's supposed to be, you have to extend that curing period by twice the number of days, or the protection period on that. Remember, what we're trying to do is grow those little crystals that are in there. So we need to maintain, by curing, enough moisture and the right temperature for that reaction to occur. So the more curing, that's better. One of the talks is, and I was fortunate to listen to Ken Hover address the issue, and he brought a problem up without a solution, is that in colder weather, we want to maintain moisture in there so it gains strength. The problem is when we maintain moisture in and it gets cold and subject to early freezing and thaw cycles, we can hurt the durability of it. So this is a very, very difficult thing to do, is to maintain durable concrete when it's subject to early age freezing thaw cycles without maintaining it above freezing. And okay, if you're having a building and you're inside, you can maintain everything above freezing. Building something outside, that's a very difficult thing to do. And he just kind of brought to bear the problems that we have out there, both maintaining moisture in that for strength gain, and at the same time, you know, maintaining temperature and not causing early age damage or freezing or thawing.
Another question came in about maturity meters. What are your thoughts on maturity meters and predicting strength in cold weather?
They're used very often on jobs like we saw on that one slide to determine when you can remove your forms, when it's safe to go over to the next level. You need to do a lot of correlation testing prior to using them to dial in your mix as to what the results that you're going to get them. It's an expensive way of doing things because to do it properly you need all that correlation. So it's usually confined to use on a job such as we saw, where it's very important for both safety and construction efficiency that we really need to know how that concrete, what is being strength is gained on that before we can move on to the next level. So that's where you'll see them used more often. High-rise construction, very important structures like that, it's worth to put the dollars in to do that. Remember, you have to correlate that very well before you can use it.
One more. If you're pouring interior in the winter, how do you know you have a properly ventilated space where you won't get crazing?
That's a very difficult question to determine. What you want to make sure is you've got plenty of fresh air coming in. The old rule of thumb was, I don't want to smell anything when I walk into that room. I don't want those heaters directly pouring onto that concrete. I want to heat the mass of everything else that's around me up to temperature first. So I'm not relying on cranking tons of combustion in there on the freshly set concrete. There's where our problem's coming in, is all that combustion directed and the product of combustion directed right at the fresh concrete. There's where we run into issues. Now, if you got that building, that basement nice and warm before you pour, that's the ideal way to do it.
That's all I got, Jim.
All right, well, we're right on time today. Thank everybody for joining us. Hope to see everybody and talk to everybody next week on December 5th on our ASR webinar. A copy of the webinar will be available on our website, and we'll also send you a link, a copy for the recording for everybody who attended today. Thank you, and good afternoon.